Our next topic or subtopic, having talked about the enthalpy of combustion, our next topic, our next subtopic will be the enthalpy of neutralization. I promised to look at some 4 enthalpies, all 5, the enthalpy of neutralization, combustion, displacement, precipitation, and solution. So this becomes our second enthalpy that we shall look at in detail, and that is the enthalpy of neutralization. The first question we ask ourselves is, what is enthalpy of neutralization? Now, as we are already aware of this term, neutralization, it was defined in Form 1 or Form 2. We said that neutralization is a reaction between an acid and a base to form a salt and water only. So one thing is going to be common to all neutralization reaction, that we are going to form water. The salts are going to be different. Sodium chloride, sodium sulfate, sodium carbonate, they are all going to be different. But all of them are going to form water. So when we get to defining the enthalpy of neutralization, we shall zero in on water as our reference. So what do we say the enthalpy of neutralization is? We define the enthalpy of neutralization as the energy involved. We'll discover that neutralization is always exothermic. So you could say the energy produced when an acid reacts with a base to form 1 mole of water. So if the other thing that I need to note is that for all strong acid, strong base pair, the enthalpy of neutralization is going to be the same, because the reaction is basically the hydrogen ion with the hydroxide to form water. Whatever else you have will just be spectator ions. Now let's think about the reaction between sodium hydroxide, for instance, and sulfuric 6 acid to form sodium sulfate plus water. 2 moles of that, 2 moles of that. When you write the ionic equation, of course you shall 2 sodium ions plus 2 hydroxide ions plus 2 hydrogen ions plus the sulfate ion to form 2 sodium ions plus the sulfate ion plus 2 waters. So the sodium and the sodium will cancel. The sulfate and the sulfate will just cancel. So what are you left with? You are left with 2 of the OH ions plus 2 of the hydrogen ions to form 2H2O. So if you had 1 mole of sulfuric acid, you realize that you're going to get 2 moles of water. But what is enthalpy of neutralization? You must get 1 mole of water. So whatever energy you get from this reaction, if you started with 1 mole of sulfuric acid, you have to divide that by 2, because it has to be per mole of water. So actually all this cancels. So all the strong acid, strong base pair will give you the same amount of energy, because the reaction involved is simply the hydrogen and the hydroxide ions are reacting to form a mole of water. Now, but what about if one or both are weak? Now you realize that the enthalpy of a reaction is going to be low. Now let me remind you what we mean by weak acid and weak bases. It is said to be weak if it undergoes partial ionization. If it undergoes partial, and that's a reminder from acid, base, and salt. If an acid undergoes partial ionization, then it's going to be said to be a weak acid. For example, ethanoic acid will ionize reversibly to form the ethanoate ion plus the hydrogen ion. But this is partial. That is partial. So we have very few of the hydrogen ions. So the question that we ask ourselves is, why is it that when you neutralize the ethanoic acid, it is going to give you a lower enthalpy of neutralization? And somebody is going to immediately tell me that we have very few hydrogen ions. So you are going to get very little water. But then the question is, does that become enthalpy of neutralization? Is that enthalpy of neutralization? If you're not going to get 1 mole of water, then you're not talking about enthalpy of neutralization. So at the end of the day, you must get 1 mole of water. But so what is the situation here? You have very few of the hydrogen ions. So what will happen is that these few hydrogen ions will react with OH to give you water. So energy is going to be produced. But now, instead of that energy being given off to the surrounding, because that is what we expect to happen, this energy is going to be taken back to the system so that you can ionize the ethanoic acid to form all of the hydrogen ions. So not all the energy produced is being given off to the surrounding. Some of the energy is being used to ionize the ethanoic acid. So you are not going to get as much energy as when you had all the hydrogen ions ionized, like in the case of the strong acids. You already have a mole of hydrogen ions. If you are using 1 liter of 1 molar hydrochloric acid, you already have 1 mole of hydrogen ions. So whatever energy that is produced is given off to the surrounding. But in this case, with ethanoic acid, you have very few of the hydrogen ions, yet you must get 1 mole of hydrogen ions. So you will use some energy to ionize it. You use some energy. So what do you want us to explain that? It is important to note that because it's a weak acid, therefore, so what? That is a question I ask people. If you tell me simply it is a weak acid, I ask you, so what? And you think I am rude. Well, you have not explained anything. So what if it's a weak acid, so it is partially ionized. Therefore, being partially ionized, yet I have to get 1 mole of water. So some energy is going to be used to ionize the ethanoic acid. We can tackle an example. Now I've already done one for us. We can tackle that simple example of working out the enthalpy of neutralization because the idea now is to work out enthalpies from empirical data. So the question is, calculate the enthalpy of neutralization of sodium hydroxide given that 20 cubic centimeters of 1.5 molar sodium hydroxide at 22 was added to 30 cubic centimeters of 1.5 molar hydrochloric acid at 23.5. They were mixed together, the temperature rose to 29. Now we know the process by now. The first thing is to, number one, get the mass. What did we say about getting the mass? Follow your thermometer. That thermometer, what is surrounding the thermometer? What is surrounding the thermometer? Now when you visualize this one, I think the thermometer is surrounded by the mixture of sodium hydroxide and the hydrochloric acid. That is what's surrounding it. That is the 20 cubic centimeters of 1 molar sodium hydroxide and 30 cubic centimeters of 1.5 molar hydrochloric acid. So I add them up to get the value of M. Of course, it is 50 cubic centimeters multiplied by the density, assuming that the density of the solid is equal to the density of water. That is 50 grams. Now the initial temperature. Now I am mixing 20 cubic centimeters, which is at 22, with 30, which is at 1.5. So if there was no reaction, what would be the temperature of the mixture? What if they were not reacting? What would be the temperature? And I just got the average. I added 20 times 22, the 20 times 22, and then added to 30 times 30, 23.5, the 30 at that, then I divided by 50. If they were the same volume, I would have just added 22 to 23.5 and divided by 2. But now I have to use the ratios of the volumes. So I'm getting 22.5, and that's something that you need to you can easily do. So the change in temperature, of course, is the difference between those two. The initial that I've worked out here minus the final, that's come 29, 6.1. Remember we said that the delta T in Kelvin is equal to the delta T in degrees Celsius. So I can easily equate that. So I already have the M, I already have the delta T. So I multiply the K and K cancel. Note that the C was given in joules per gram per Kelvin. So this must be in grams. So the G and G cancels. Then whatever remains is going to be in joules. Now the next part of that is to calculate the amount of substance that is reacting. So we said get the amount of heat, get the mass, get the temperature change, and temperature change is not equal to heat change. Because I've seen some students who have been asked in an exam, calculate the heat change, and they just go on to calculate the temperature change. Now that is vernacular. The vernacular, you can think about it in your vernacular and see whether you are not thinking in vernacular. Temperature change and heat change are two different things. Although one will point to another. You use the temperature change to calculate the heat change, but they are not the same thing. So this is temperature change and not heat change. So we go on now once you have the heat change, the temperature, the mass, that can help you get the heat change, which is actually that much. But now the next step of that was to get the amount of stuff that is producing that heat. Not that I want to get the amount of the enthalpy of neutralization. So it's supposed to be per mole of water. So I ask myself, how many moles of water are formed? When sodium hydroxide react with hydrochloric acid, 1 mole of water is formed. I can balance that equation. 1 mole of water is formed. So the reacting ratio is 1 to 1 to 1 to 1 throughout. So whatever moles of sodium hydroxide I get, if it's 1, then I have 1 mole of water. Whatever moles of hydrochloric acid, it's 1, then I'll have 1. So I can use any of them. Although in this case, when I look at this, the ratio is supposed to be 1 to 1. I think then there are less moles here than the number of moles here. So it means that this is in excess. I cannot use the one that is in excess. It did not react completely. That is why I strictly go for the sodium. So you have to think about which of the two to use, because you could use this or that, but now this is in excess. 30 of 1.5, 20 of 1.5. So this is less than this. So this react completely, this does not react completely. You can convince yourself. So I'm going to use this, convert that to moles. Yeah, you can use the expressions or say 1,000 cubic centimeters contains 1.5. What about 20? It is going to come to that, and that is what is giving me 0.03. So that is what is producing this amount of energy. So what about 1 mole? Note, it is negative. Why? There is an increase in temperature of the surrounding. Energy is being given off to the surrounding. So it's negative in kilojoules per mole. So the units and the sign must be shown. Otherwise, you're going to lose half a mark. Can you attempt another question, maybe? And if you are comfortable with it, you can pause the video and go through it. I hope you'll be able to overlook the answer, and then, but that is what you should get. You can pause and do it, see whether you are going to, you can write the question, do it and see whether you are going to get to that. But what have I done? Assuming you are back from the pause. Now I was given 4.2 kilojoules per kilogram per Kelvin. So I have to convert the 45. 45 we may talk happy. Where is it coming from? 20 plus 25. Whatever surrounds the thermometer. 20 and 25. So the temperature rose by 6. So that is in kilograms. Now must be in kilogram per kilogram. So 45 grams divided by 1,000. That will be in kilograms. Then times what is this? Kilojoules per kilogram per Kelvin. And cancel, that is what I get from that. Now I have written the equation here. Okay, so what do I have here? That this reaction is forming 2 moles of water. But for every mole of water, that is the amount of energy that should be produced. So whatever I have here is per mole of water. Kilojoules per per mole of water. That should be somewhere at the back of your mind. So for every mole of water, I have that. So this energy that I've gotten here, MC delta T, how many moles are those? Now these are the moles of water. But what about moles of sulfuric acid? They should be half. They should be half. So divide that by 2. Those number of moles are the ones that are in 20. 20. So what about 1,000? And I think that is what I get. Now, having said that, the next thing I'll do is I'll take us through an experiment to determine the enthalpy of neutralization. And what? In this experiment, the enthalpy of neutralization of sodium hydroxide shall be determined. Now, all I need is 1 molar hydrochloric acid and some sodium hydroxide. What apparatus do you think I'll need? Definitely I'll need a thermometer, a plastic beaker. Yes, because I'll have to mix. I need some measuring apparatus. I'll need some apparatus to measure volumes, for example. I'll need to measure some volumes. Yeah, maybe I want to take 20 of that and that. So I need some measuring apparatus and all that. But what is the procedure I want to adopt? Because I want to do a graph. Now this is a procedure I want to adopt. I'll put some hydrochloric acid, the 1 molar hydrochloric acid, put it in a beaker. Put it in a beaker, and then to put it in a burette first. Then I have been told to take 16 cubic centimeters of that, and to that I'll add 4 cubic centimeters of sodium hydroxide. So I'll use a measuring cylinder to measure 4. I'll measure from the beaker the 16. I will determine the temperature, the initial temperature of whatever that is in this beaker. Measure the initial temperature of that. I hope you are following. Measure the initial temperature of the whatever is in this beaker. Then add 4 cubic centimeters of sodium hydroxide. Record the maximum temperature that has been attained and record it in a table. So in fact, in this experiment, I want you to look at the thermometer now. I'll be adding the volumes for you, but you will be the one to pick up to read the thermometer, because it's very important that you familiarize yourself with the thermometer. It's only that I could not invite you to come and do the mixing, but now reading the temperatures from the thermometer is a skill that you need to acquire. So take time and look at that, and then you record in a table. So what are you recording? So the 4 mixed with 16. Now the 4, what is the temperature of that? Record it. That is the 16. The volume of the hydrochloric acid, the 16. You are measuring its temperature, so you record it there. Now then when you mix the 4, you record the highest temperature reached. So you need to be very fast, because sometimes the temperature rises and then starts to drop. So take note of the highest temperature, then record it there. Then the next experiment, you shall mix 8 with 12. 12 from the burette, 8, and that has been done for you. So all you need to do is to record that temperature, and you will do all that and complete that table. Now the question before you even do that, I need to ask you, what are you expecting? Because your theory and the practical must agree. You cannot just take muscles to the lab. You need to be expecting something, so that if you don't expect that, you can either repeat, you may need to redo. Of course, in this particular experiment, I expect all the 4 to react. I think I have excess of this substance. So I expect all the 4 to react. All the 4 must react, so there will be a change. And maybe even in this one, all the 8 are going to react. So the temperature change here should be higher than the temperature change here. Now in this one, probably, I think most probably, I have more of this one than the other one. So all these will react, not all these will react. So I don't think the temperature change here should be higher than the temperature change here. I don't think it should be. So if I discover it's more, then there could be a small problem. So the temperature should rise, but should then start to fall, because now I have reversed. All this will react, but not all this is going to react. So the temperature change should be lower than maybe when around here, when I had maybe all the 8 and maybe all the 12 reacting and all that type of so there should be a rise in temperature followed by a drop in temperature. So you need to have that in mind as you do the experiment, because sometimes the experiment refuses to agree with your theory. It means that there is a mistake somewhere, then therefore you need to either redo the experiment or adjust your data accordingly. I'm not teaching anybody to cheat, so I am suggesting you redo. So let me get back to this table. You need to watch the creep. So copy the table, watch the creep, and complete that table. Complete that table. Do complete that table, and we shall use it. So in this experiment, the enthalpy of neutralization of sodium hydroxide will be determined. So I will be mixing different volumes of hydrochloric acid with different volumes of sodium hydroxide and noting the temperature. I have a table that you will be filling in. I've started by measuring some 16 cubic centimeters of solution C, which is hydrochloric acid, and pressed it in a beaker. So you are expected to read the temperature of that solution, and you can do that and record in the table provided. Then I've also measured some 4 cubic centimeters of the sodium hydroxide, which I'll add to the 16 cubic centimeters of the hydrochloric acid. Please note the maximum temperature reached. Note the maximum temperature reached and record in the table. In the second experiment, we shall measure 12 cubic centimeters of solution C, that is the hydrochloric acid, from 16 to 28. Be very careful how you use it, the burette, up to 28. We want to get the temperature of that solution and record in our table. Get the temperature of the solution. Record that in your table. Then to that I will add 8 cubic centimeters of the sodium hydroxide. How do you take your readings? Show your readings, your parallel to the ground. So mix them and note the highest temperature reached. Shaking so that you can have uniform uniform distribution of the temperature is uniformly distributed. Now the next experiment, we shall pour that and from the burette we shall measure 8 cubic centimeters. So from 28 to 36. then we shall get the temperature of that. Record in your table the initial temperature of that solution. And for the sodium hydroxide, we shall measure 12. And definitely mix, start to get a uniform distribution of that. Please get the highest temperature reached and record the highest temperature reached. Now for the next experiment, we shall have 14 cubic centimeters of the... Now let's start with this so that we can be measuring its initial temperature. So we shall use 6 from 36 to 42. Now read the temperature. To that I'll need to add 14. Hope you have taken that initial temperature, 14, shake well, and read the maximum temperature. Record the maximum temperature attained, and I'll need a 16 of that. Can't discard that, of course. Then I will take 4 from 42 to 46. We need to take that initial temperature and record it. Then I'll add the 16. We need to record the highest temperature reached. Record the highest temperature. The other one will be 18. Assuming that is red, can discard this. Use it to measure 2. So from 46 to 48. You need to also get the initial temperature of that solution for free. Then once that's recorded, you can add the 18. Shake well and take the maximum temperature. Then complete the table by working out the change in temperature. use the data obtained to draw the graph and consequently to answer the questions as will be given. Thank you. So, this is the data that I got from the experiment. Now, when you get data like this, it will always be marked. In fact, this is where marks are. That can carry around six marks. It is usually very generously awarded. 6 marks, you don't get 6 marks every other day. So, but where do we get those marks? For completing the table, actually doing the experiment, you will get yourself 3 marks first. When I look at your table and it is complete, I will give you 3 marks. I'll theoretically give you 3 marks as I look for some place where I can penalize. For instance, I may penalize if you have not subtracted properly. There is a subtraction to be done here. If you have an error in subtraction, I can subtract half a mark at most. Even if you make errors everywhere, I'll only subtract half a mark and give you 2.5. So you are lucky with 2.5. However, I will penalize a half a mark for any experiment that has not been done. There is a way of looking at your data and now we'll know that you did not do the experiment. For instance, supposing your initial temperatures are too high or too low, like temperatures of 10. I'll ask myself, is this guy based in the northern hemisphere, or is he somewhere around the Arctic? Yeah, because how can he get 10? In fact, you see somebody with zeros throughout. So if you get 0, 0, 0, 0 for any experiment that is not done, I will penalize half a mark. So the 3 can all go. Because if you start from 0 there, then it has not been, you did not do that experiment. You start from 0 there, or you start from a value like 40. Hey, are you still alive? Where are you working from? From the kitchen, from inside the fire, or even if you are in the desert? I don't expect the initial temperatures to be anywhere above 40. Especially because you are measuring the temperature of water. The room temperature, I'm told sometimes when there is a heat wave, can be 40, but that is very uncomfortable. I think you should be more of in the hospital than in the lab if the temperatures are 40. But even then, the temperature of the syringe cannot get to 40. The water cannot get to 40. So anything above 40, I will know you did not do. So familiarize yourself with the apparatus and don't guess. Work out the values. Now, delta T is above 10. I don't expect delta T is above 10 in this particular experiment. So anything above 10, I will know you did not do the experiment. So I'll award accordingly. So you have above 10 there, but below 10, then I will. So that is how I will know that you did not actually do the experiment. So learn to use your apparatus and record. And I think temperatures like you'll get, how can this come to below 10? Because some people will read this, instead of saying 20.5, they will read it as 2.05. So you know that the temperature, the thermometer has values 10, 20, so you can, all that. So that's, if you read this as 1, then instead of 10, so 11, 12, 13. So you cannot read 1.0, 1.05 and all that. So that you read to me knowing that you did not do the experiment. So I will penalize the 3 marks that are supposed to be actually free. Now where is the other mark? The decimal mark. The other mark is the decimal mark where, so when you use the thermometer, you can only read the thermometer either to 1 decimal place or to whole numbers. So I can write 20, 22, 24, 23 and all. I can write in whole numbers, but I must not mix decimal. The moment I have 20.5, then I have to write all the others 21.0 and not just 21. If I mix decimals, that would be wrong. If I write So if I can use one decimal place, all whole numbers, don't mix them. The other thing, you must not use two decimals for the thermometer. How do you tell me that you can read 20.00? You cannot read the second decimal. You cannot be read, because I cannot read 11, 12, 13, 14. And again, if you're using one decimal, then it can only be 20.5 or 20.0, not 20.3, unless you have a magnifying glasses inside your eye. Are you the same family as a cobra? I am told they have magnifying glasses in their eyes, so they see a giant you. I don't think you have that ability. So you cannot read 20.3. You are telling me that it is somewhere here, but it has not gotten to 5. It is just somewhere between 0.5. Hey, that is not possible. So if you are writing one decimal place, it has to be either 0 or 5. If you don't write 0 or 5, then you lose that decimal mark, and it's a full mark. It's either 1 or 0. Now the other one is at the accuracy, and everybody gets the accuracy mark because it is marked at this point. At this point, the initial, it will be marked for the initial. So that is the temperature that you took your time to determine. If it is 21, if your teacher read 21 and you have 23, you get the full mark. If you have 19, you get the full mark because it's plus or minus 2. Hey, that's a very big range. That's a very big range. So between that 21, 22, 23, 24, 22 and 19, all this range, you cannot miss it unless you don't do. So how do you ensure that you don't miss that? Ensure that your thermometer is okay by ensuring that it doesn't have a discontinuity. So some mercury has broken from the rest of the mercury, it is somewhere there. That thermometer is going to give you wrong values. Don't use it. Ask for a better thermometer and you'll always get the accuracy mark. The other mark is for the thread. That is actually theory. What am I expecting to happen here? I'm expecting an increase followed by a decrease. If you have an increase, like I think I will lose half a mark here because I have a constant. It did not consistently decrease. I've lost half a mark. I've lost half a mark. Where did the mark go? The thread. I have a constant increase, then a decrease. But there is a small constant there. It's constant there. So the half a mark has gone. I have lost half a mark because of that constant right there. But that is, so you need to marry your theory with the practical, whatever that is expected, whatever that you are doing. Let the two agree. Now the next thing that we shall need to do is to draw a graph, and of course I've drawn my graph. My graph looks like that. I hope it's visible. I hope it's visible from wherever you are. So the first thing that, how do you get these marks? Now the first thing that you need to do is, let's start with the axis. The axis. Draw the line. Draw the line. Put your arrows. I did not do that. I've lost that. Then label your axis. Label the axis. Change in temperature in degrees Celsius. Put the correct unit. Volume of sodium hydroxide in cubic centimeters. So once you've done that, you already have a mark. The half a mark will be lost if, now that you are told to draw this on the axis and that on the, if you interchange them, the mark goes. You don't remember to indicate that that's volume and that is. The mark goes, you have not labeled your axis. Anyway, so now we talk about the scale. The scale is the area occupied by your plot. Does it cover half of the paper? Does it cover half of the paper? And it's a plot. Not whether I've written 5, 6, and 7. No, I'm not interested in that. I'm interested in the area covered by your plot. This is your first plot, and this is my last plot. 1, 2, 3 boxes out of 1, 2, 3, 4, 5, 6. So I am safe. The graph has occupied half. Of course, I could have made it bigger if I did 1, 2, 3. But that's very risky. Because how do I extrapolate? How do I extrapolate? It is going to get outside that range. So that's why I decided to just use half, and I'm still safe. I still have the mark. The other option was maybe to use 1.5 or 1.5, 3, 4.5. That was an option. But a scale of 1.53, you'll always have to round off when you plot. So you should avoid that. If you cannot divide exactly the 20, 20 divided by 1.5, you cannot divide exactly, so avoid that. So you don't know the value of one of the box. So you need to avoid such plots, because you have to round off when you plot. You're going to lose the plotting mark. Now the other thing about the scale, now that is the size. Does the scale accommodate all your plots? Yes, it does. Is the scale consistent? So like 4, 6, 8, 10, 12, 14, 16, 18. Of course, when you look at the table, it was 4. The other one was 8. So some students will be tempted to bring the 8 here. You'll be tempted to bring the 8 here. In which case, you have lost the consistent mark. You'll even lose the plotting mark. So there has to be a scale. There has to be a scale. Now, what is the next thing that I need to do is to plot. There will be a full mark for the plot. If you plot all of them, if you only have one wrong plot, then you have a full mark. If you lose 2 plots, then you lose half of the mark. 2 plots are wrong, you lose half of the mark. If you have more than those plots wrong, then you lose all the plotting marks. Now, you need to plot your plots as accurately as your scale can allow. As accurately as your scale can allow. If, like, you see, I have seen students who even lose a plot for even not being able to plot the 14. Just slightly outside the 14. And that's where the examiner starts from. Looking at whether you have plotted the 16, the 14, the 12. Because that is very easy to see from very far. If it just moves slightly from this board line, then that's wrong. And you see, I'm counting the number of wrong plots, and if I get more than 2, then I don't have to proceed to the other plot. Now, it is very important to note this. Now, supposing I did not, supposing I wrote a big 0 there. A big 0 there. I don't like that 4. I don't like that 4. And I have a big 0 there. Then I have a 6 there. Now, there will be a problem with this plot. There will be a problem with this plot because from 0 to 6, those are 6 units. 6 to 8, those are 2 units. Those are 2 units. So I will have a problem with the scale. I'll only be allowed to plot values in this first scale. And there is only one. There's only one. So when the scale changes, you only can plot in the first scale. So what if I did not want to do that? I wanted to put a 6 there, or I wanted to put a 4 there, and then continue. Then I had to break because I have a big 0 there. But if I put the 0 somewhere there, I don't put anything there, then I'll be given the benefit of doubt. The examiner will assume that I started from 2, I started from 2 so that I get the scale. But if I have a big 0, then I've already committed myself. So this side is starting from 0, that side is also starting from 0. So I'll lose the plotting marks, and that also risks the loss of the curve mark. Now the next thing, the lines. There's one mark for the line. They have to be straight lines. They have to be straight lines. And remember, any 2 plots are enough to make a straight line. Any 2 plots. So I use those two, I get a straight line. Now for the others, I have more options. I could have chosen this and this. Now if I choose that, and I tried it, it was a straight line and I have actually joined 3 points. But there's something completely wrong with that. What is that? My lines are meeting at a plot. When lines meet at a plot, they are not extrapolated. If they meet at a plot, they are not extrapolated, so I get a 0. Now what is the other option? I could have used this and this, alright? Okay, I've used that and I've gotten that. Supposing I use this and that, what do I get? Get a line that looks like that. If the lines are now meeting, the two lines are meeting below the highest plot, so that's also wrong. So for you to say that the lines are extrapolated, they must meet above the highest. They must not meet on a plot. They must not meet at a plot, and they must meet above the. Those are the two conditions. Not at a plot and also above, not below. So my best choice was the line that I've just drawn. The line that I've just drawn. So you can get the data, whatever data you got, and make sure that you compare your graph with the graph that I get, and that is it. So the next thing that I will do is to use the graph. So what was I required to do from the graph? The first thing is to determine from the graph the maximum change in temperature. Back to the graph, the significance of this point. This is the neutralization point. That is a neutralization point. This volume, this is a neutralization, the volume that's of sodium hydroxide is required to neutralize the hydrochloric acid, and this is the maximum change in temperature. So this point is very important. It is the neutralization. That is a neutralization point. It is the end point. This is the end point. So I can read the volume required, and I've read it. I got to 8.5. Please show. Always show. Now for two reasons, it is easier to read when you have shown. There's something that is called parallax. You are trying to follow it, to follow, then you get somewhere, you blink. When you blink, you lose. You have to start afresh. Why do you struggle? Just get a line, a ruler, or a straight edge. Draw a dotted line. That will be easy. You can easily read that. That is one reason. The second reason is, if you show and then you don't read correctly, you'll get half a mark for showing. You'll lose a mark for the reading, but you'll have at least have scored half a mark for the showing. So it's advantageous to use. It helps you, and also it can earn you. Of course, if you don't show but you read correctly, you still get the full mark. But you really have to struggle. Then I got 8.5 there. Then I got around 3.15 for that value, and that's an interesting one, because when I show, I have a 3.15, but when I read, I may decide to use 3.2. I have shown correctly, but I've read wrongly, so I still have half a mark. So those are the data, the piece of data. So the temperature, the maximum temperature change, that's the neutralization temperature, and then the volume of sodium hydroxide that is required can easily be read from a correct graph. Note, the graph must be correct. If the graph is wrong, then you can't use it. If it's not extrapolated, then you cannot use your graph, your wrong graph. You will not get these 2 marks if you did not get C is equal to 1. If you didn't get 1 mark for the C, then these 2 marks you will not get. But if you use your wrong values correctly in the questions, then you'll get the full mark. So what is the first thing that is required of me? The number of moles of hydrochloric acid required to give the maximum change in temperature. Note, according to the to the procedure, when you add 16 to 4, that is 20. When you add 4, look at your table, they are all adding to 20. They are all adding to 20. That is the nature of that procedure. So even in this one, at neutralization, I'm using 8.5 of sodium hydroxide. So what volume of hydrochloric acid must I use? The volume must add up to 20, so I'm using 11.5. I'm subtracting from 20. But I was given that the acid was 1 molar, so I can get the number of moles in the volume that is used, the neutralization volume, and that is 0.115 moles. If you write units, they must be correct. If you don't write units, you still get the answer, because the units are definitely implied in the question. Note that we don't have that M is not short for moles. It's actually short for meters. So did you use a meter rule to measure concentration? So small m is not moles. Small m is, so if you want to shorten moles, you write MOL. If you write MOL, you cannot put an S. It becomes a wrong unit. So, because you don't write meters like that, do you? If you do, then go on to write the plural of the shortened form. So, moles, this is around, mole is around, mole is not around, moles is not around. All those are wrong units. So, let's get back to calculating the molar enthalpy of neutralization, so per mole of water. Now, the first thing is get the amount of energy that is produced, MC delta T. What is M? Now, there are two questions that you've done previously. The M value was the total volume at neutralization. That is what we are using. The thermometer is surrounded by the volume at neutralization. So, in this case, in each of the experiment, it is 20, it is 20, it is 20, it's 20. So 20 becomes my M value times 4.2 joules per gram per Kelvin times the change in temperature. The K and K cancel, the G and G cancel. So whatever I get therefore will be in joules. Whatever I get will be in joules. So after that, what about, so this one is produced by the moles I've calculated in the previous, moles of hydrochloric acid. That's what, of course, 1 mole of hydrochloric acid produces 1 mole of water. The ratio is 1 to 1. It's monobasic, so it's going to produce 1 mole of water. So for 1 mole of water, that is the amount of energy. It's negative. There's an increase in temperature. Kilojoules per mole. The answer was, you must give the answer in kilojoules. Kilojoules per mole. So you lose a mark for not dividing by 1,000, whatever you get here. You lose a mark for not indicating the negative. You lose a mark for not indicating that it's kilojoules per mole. If the units are not there, all are wrong, you lose a mark. Oh, 23, compare that with the theoretical value of 57.2. That is extremely low. Why is it too low? Now, first I used a glass beaker. Why didn't I use a plastic beaker? I wanted you to see what is happening. Maybe, hey, that's clever. A glass beaker, it's going to be a better conductor. A lot of heat losses to the surrounding, heat losses by convection and all that. And of course, apart from the heat losses, there are also the assumption that the specific heat capacity of the solution is equal to the specific heat capacity of water. That assumption, whatever solution I get will not have the same density and the specific heat capacity as that of water, but I've assumed them to be the same. So those are two sources of error for that particular question. So I will give another example, then you can also attempt that question. Now you got that answer. Construct an energy level diagram for the same. So you write the thermochemical equation. And draw energy level diagram. Get to that. Write a thermochemical equation and draw an energy level diagram. If you can do that, let's meet in the heat of, as you calculate the enthalpy of displacement.